All right, so lesson 3 then is independent and dependent events. So we're still going to be working with probabilities, but we're going to talk about specifically independent and dependent events. In reality, there's not a lot different about them, okay, for the most part. Okay, independent events are if the occurrence of one event does not affect the probability of another. So for instance, if I flip a coin once, okay, and then I flip a coin a second time, does the result from the first flip affect the result from the second flip? No. Okay, so those would be independent events. Okay, if I take a deck of cards and I shuffle a deck of cards and I put a card down, pull it out, set it down, and it's the Queen of Hearts. Okay? All right. Now, if I pick it up, put it back in my deck, shuffle it up, and put another one down, is the probability of getting the Queen of Hearts any different? No. Okay? So those would be independent events. Now, if I left that card down on the table, shuffled them, and pulled another one out, is the probability still the same? No. Okay? It's not. It changes. So independent events where that probability would be the same, dependent events are where that probability changes, okay? But we end up multiplying in either case. So, all right? So if A and B are independent events, then the probability that A and B both happen is the probability of A times the probability of B. And I just realized I'm missing something. My smileys are gone.
And you're recording.
And I am recording it. So I'm going to have to figure that out. You know what? That's not a good thing. Okay? All right. So finding the probability of independent events. Six-sided cube is labeled with the numbers 1, 2, 2, 3, 3, and 3 again. Four sides are colored red. One side is white and one side is yellow. Find the probability. Find each probability. So what is the probability that we toss this number cube and we get a 2? What's that probability? So the probability of getting a 2 is equal to what? There's 2 of the 6 are a 2, so that would be 1/3. Okay? All right. So I take that number cube and I roll it again or toss it again. What's the probability I get a 2 the second time? 1/3 again. Okay? So what I'm doing here is I want to find the probability of getting a 2 and then getting a 2 again, which would be 1/3 times 1/3 or 1/9. For all you purple lover and crayon people. Okay? All right? Okay? Now we're on the same, using the same number cube, or same cube. We want to know the probability of tossing a red, then a white, then a yellow. So that means we're going to do probability of red and white and yellow. Okay? So we need to find the probability of all 3 of them, and then we're going to multiply them together. Right? So it's very similar to the fundamental counting principle. Okay? So red, what's probability of a red?
2/3.
Okay, there's 4 of them out of the 6, so that would be 2/3. So red is 2/3. All right, and we're going to multiply that by, what's the probability of a white one? 1/6, and if I wrote with a white up here, we wouldn't get it, so we'll say 1/6 there. And what's the probability of a yellow? 1/6. So let's change that to yellow. So that'll be 1/6. All right, and that equals what? Let's see. 6 times 6 is 36, right? And times 3 is 108. Okay, so we would have 2 over 108, which is 1 over 54. And we'll circle that one with the red crayon. Okay, dependent events. If the occurrence of one event affects the occurrence of another event, all right, here we go. All right. Okay. Then the events are dependent. So for instance, like here, this person has 3 pieces of fruit in a bag, 2 lemons and a lime. Okay. If I take the first fruit out, I have 2/3 of chance of getting a lemon and 1/3 of a lime. Okay. Now, this is where sometimes that good old tree diagram comes into play. That if I pull a lemon out, well, how many pieces of fruit do I have in there now? Just 2. Okay. Half of them are lemons and half of them are limes. Okay. And if the lime comes out, then I have just 2 lemons, so there's a 100% chance of getting a lemon then. Right? So we're also going to use something called conditional probability, okay? And that's the probability of B given A, which means that the event A happened first, and then event B is going to happen. So in other words, we would say, so what would be the result if I got a lemon and then a lime? Okay, and so you would have to take the fact of getting a lemon first affects what happens after that. So here's how that works. If we have probability of dependent events, if A and B are dependent events, then the probability of A and B is equal to the probability of A times the probability of B given A. Okay? And that just means then that you have to take that first thing into account to get the second thing. So let's see how it works. All right, let's go to our So we've got our friend here, the rolling 2 number cubes together. All right. So we want to find the probability of dependent events. So 2 number cubes are rolled, 1 white and 1 yellow. And so we're going to say that these are blue and red. Okay. All right. So instead of white, we're going to use blue. Instead of red, instead of yellow, we're using red. Okay. Explain why the events are dependent, then find the indicated probability. Okay. So letter A, the sum is greater than 9, and the blue cube shows a 6. Okay. Sum is greater than 9, and the blue cube shows a 6. So first of all, we got to explain why the events are dependent. Okay. So first we have to look at sum is greater than 9. Okay. So what's the probability we have a sum greater than 9? Let's see, greater than 9 would be, oops, we can't use that color. Greater than 9 would be these, oops, not those. Those right there, right? 6 out of 36. They have a sum greater than 9, don't they? No. Okay, all right. First of all, we're focusing on the first part, okay? We're focusing just on this part here, first of all. Sum is greater than 9, okay? And that happens on 6 out of 36, right? So that probability is, oh, you're not doing this to me. Okay. All right. That probability is 1/6. 6 out of 36 or 1/6. Okay? All right. Now we're going to look at, okay, the probability that the sum is greater than 9 and the blue has a 6. So now we're only focusing on just those 6 now. Okay? We're not worried about anything else because we're only focusing on those 6 because we said sum is greater than 9. That's a given. Okay? And now we're looking at the blue cube shows a 6. So how many of those sums greater than 9 do the blue one have a 6? 3. So that probability is going to be 3 out of 6. Okay. All right. And here's one thing that will always be true. Okay. That one thing that's always true is that this number here and this number here will always be the same. Okay? Those will always be the same. The numerator for the first part and the denominator for the second part are always going to be the same. So, is 1/6 equal to 1/2? Okay? If these two things are equal, they're independent. Okay? If they're not equal, then they're dependent. So we just showed that these are dependent because these two probabilities are not the same. Okay? So now, to find the probability, we're going to multiply them together. So we get 1/6 times 1/2, you get 1/12. Now, how many of you came up with 1/12 earlier already? Already figured out 1/12. Okay, Justin did. All right. Because if I look at this, go back to this chart here. If I go back to the chart, we've got, out of those ones that we circled, okay, there were 3 of them that have a sum greater than 9 that had a blue 6, right? And 3 out of the total is 36, and 336 is 1/12. Okay? So could the answer have been found without all that? Yes, it could. Okay? But I need to prove that they're dependent, first of all. So I did need to look at those values. All right? Okay. Let's see, the yellow cube, so the red one, right? Okay, the red cube shows an even number. Red. Okay. All right. The red cube shows an even number, and the sum is 5. Okay. So first of all, we got to find red has an even number. How many of those red ones have an even number? Okay. Half of them, right? Okay. 2, 2, 2, 2, 2, 2, 4s, and 6s. So this probability here then is going to be 18 out of 36, or 1/2. Okay. So now we are focusing on just these 18. All right? We only care about that the red is an even number. Okay? How many of those reds with even numbers? So our denominator here is 18. Okay? How many of those have a sum of 5? Okay? We have 2, 3, and 4, 1, right? So 2 out of 18, which is 1/9. All right? So since these are not equal, okay, they're dependent events. And then so to find the probability, we multiply 1/2 times 1/9 and get 1/18. Or we could look at it as that we've got, let's try the yellow. We've got this one here and this one here, which would be 2 out of 36, which is 1/18. Okay? All right, that's a nice bright yellow, isn't it? All right. So conditional probability often applies when data falls into categories. So here this table shows domestic migration from 1995 to 2000. A person is randomly selected, find each probability. So what's an immigrant? Okay, a person that moves in, and an emigrant, okay, is someone who leaves, okay. All right. So what's the probability that an immigrant is from the West? Okay. So here's what we want to do then. We want to focus on, first of all, we want to focus on the immigrants. So how many immigrants are there? How many? 11,656. Okay, so my denominator here is 11,656. Okay. And how many of them are from the West? Okay, 2,654. And so in this case, then, we can go ahead and find the decimal. So what decimal is that? And we have big fractions like this, a decimal is appropriate. So this is approximately what?
4.4.
Why don't you try dividing the other way, Justin? Right. The numerator goes on top.
I got 0.23.
Okay, 0.23. Okay, so there's about almost 25% of them are from the West. Okay, what?
So did I.
Right. So if we go 2 decimal places, we'll round up. Okay. All right. Okay. So let's get rid of my highlight here. Oops. What did you say? 0.23, right? Okay. All right. Okay. That someone selected from the South region is an immigrant. Okay. So then we're going to focus on the South first of all, and then find the immigrant. So how many people then are from the South? Okay. All right, so there's 8,285, right? And then 5,042 of them are immigrants, right? Okay. Oh, so let's, all right. So we've got 5,042 over 8,285. All right, which is approximately what?
0.608.
Okay, 0.61. Okay, so approximately 61%. All right. Now, look at these two again. It says an immigrant is from the West. Somebody from the South region is an immigrant. Okay. Now, this question here, this next question then, changes that just a little bit. And so we got to pay attention to the difference. Here's the difference. It says that someone selected is an immigrant and is from the Midwest. All right. So now we are talking about everybody. Okay? Right? As soon as we throw this word "and" in here, we're talking about everybody. Okay? So out of everybody, who is an immigrant and is from the Midwest? And this is where we have to do this. It's where we've got to use the fact that we have the probability of A times the probability of B given A. We have a conditional probability as soon as we put the word "and" in there. Okay? So it's probability of an immigrant and Midwest. So this is just like the ones we did with the number cubes. Right? So what we need to do is we can look at it this way then. So we want immigrant and is from the Midwest. So we're talking now about immigrant, Midwest. We're talking about 2,951 people out of everybody. Okay? So I have to add up all of these numbers, and then it would be 2,951 out of them. Right? So we got 2,951 over what? Okay, which is approximately what decimal? Okay. All right, so about 13% of them is the case. All right, so pay attention. Once again, the difference is the word and. That word and tells me I'm working with the whole population. Where in these other two cases, the letter A, I was looking at immigrants, and then those from the West. Letter B, South, and those are immigrants. Okay? But it just says someone selected from the South region is an immigrant. Okay? The key word again is the word and. So you need to focus on that word. All right. Many cases involving random selection, events are independent when there is replacement and dependent when there's not replacement. All right? So reminder, a standard deck of cards, there are 52 of them. There are 4 suits, clubs, spades, hearts, and diamonds. And there's 13 of each of those cards. And there are 4 of each kind of card in the deck. All right? 4 aces, 4 nines, 4 queens, and so on. Okay. So 2 cards are drawn from a deck of 52. Determine whether the events are independent or dependent and find the probability. Selecting 2 hearts when the first card is replaced. And here's the key word right here. Replaced. Okay? If I pull a card out and put it back, does the probability change? No. Okay? So that means that it is independent. Because the probabilities don't change, all right? So what's the probability that I pull a card out and I get a heart? Okay? 13 out of 52, right? There are 13 hearts out of 52, okay? Which is actually 1/4. Okay? And so I put that card back in the deck, shuffle the deck up, pull another card out. What's the probability I get a heart? 1/4. So we multiply these together, and we get 1/16. 1/16 without a yellow crayon. Oh, can't see that one. So we'll cover that one up with our whatever color this is. Looks like brown. Okay? All right? All right? Selecting 2 hearts when the first card is not replaced. Okay, so there's our thing we need to know is it's not replaced. Okay? Which means that they are now dependent. All right. So I pull a card out. What's the probability I get a heart? 1/4. Okay. All right. 13 out of 52, right? Now, I set that card down. Shuffle the deck. Now what's the probability I get a heart? Well, I just pulled a heart out, right? So now there's only 12 hearts and there's only 51 cards. So this is 12 out of 51 then. Okay? So we went from 13 out of 52. Okay, so maybe you might want to write it as 13 over 52, just so you can see that I'm subtracting 1 from each then in this case, because I'm getting 2 hearts. All right? Then that changes it just a little bit, doesn't it? Okay? All right, which we're going to have that. Okay? All right, so 13 out of 52 times 12 out of 51 is what? Okay, that probably reduces. What'd you get? 1/7? No, it's not 1/7. Let's, all right, so 1 over 4 times 12 over 51, okay, which, all right, let's use our math skills here. We get a 1 here and a 3 here, and 3 goes into 51 17 times. So we get 1 over 17 and our shape recognition and yellow and all right, 1/17. Okay, all right. Let's see. A queen is drawn. It's not replaced, which means it's going to be dependent. Okay, it's not replaced, so it's dependent. All right, so now, what's the probability I get a queen? Okay, 4 out of 52. All right, so now it's not replaced. How many cards do I have now? 51. How many of them are kings? 4. Okay, so we get whatever that reduces to.
Four out of 663.
4 out of 663.